that. Now, I forgot who said this. It is absolutely true. One way to do this is collapse all 6 people, make one person do all 6 of those, and put 6 of them in parallel. We can absolutely do that. Let's not do that. Let's just focus in on just this room, and let's say, I'm going to put more resources in this room. I want it to go faster. All I'm going to do is I'm going to take whatever I have up here, I'm going to duplicate it. So I'm going to have another cubicle, I'm going to have another person, I'm going to have all the stuff associated with it. So let's go ahead and I'll leave all the rest of it the same. Let's go ahead and say, you come in the door and you either go to that cubicle or you go to this cubicle. Here's another person. Oops. There's another person, okay, and it has a nameplate. Let's assume it's exactly the same cubicle, so it's I equals RT, 1 customer, 60 customers per hour, T equals 60 seconds. All right, now we got the room. Okay? Yep. Well, so you're assuming that we had some kind of slacker person in there, right? Let's assume that they were. Now, here's a thing to be careful of. Okay? Hang on. So, Coco is fire everybody. Hang on a second. Hang on. Here's the thing you have to remember. We have almost been trained in our thinking to believe that whoever is the bottleneck is the problem, right? And I think this is what Coco's alluding to here, the idea that if you're the bottleneck, then you're a bad worker. Do you understand that's not true? There will always be a bottleneck, okay? There will always be a bottleneck. It doesn't mean you're a bad worker if you're the bottleneck. You just got assigned a shitty job in there, the one that takes too long, right? Okay? So, let's assume it's not the bad worker, okay? We're not gonna fire this worker, okay, and we're gonna keep this person. We cool?
Okay.
I'm just gonna go hire another person. Yeah.
Quick question, could you please remind me why not knowing the rate in the triangles is not a problem to calculate the utilization?
Because the triangles don't affect the most that we can run at. If we're running 60 customers an hour through that system right there, then each of those rooms is having to deal with 60 customers an hour, and so that is the correct average utilization. Okay.
Do you gain any efficiency by just rearranging the code?
So we're not rearranging, we're adding. Let's be clear. We used to only have 1 cubicle in this room. We had to go put in another cubicle and hire another person. Okay, there's 2 cubicles in that room. Is that clear? Okay, so now you'll see why we're doing the whole draw the rooms, draw the boxes, draw all the other stuff. Okay, and then for your homework, it's just one step more complicated than this. Okay, so do I have to change anything over here? Is this still I equals 1, R equals 240, and T equals 15? Not a dang thing changed there, right? But what about what's written on the outside of this room? Remember what those things mean. Let's start with T. T is, if I leave the triangle and I break the blue barrier, how long before I leave the blue barrier on the other side? It's 60 seconds. That has not changed, right? Because I'm either going to spend 60 seconds in this cubicle or I'm going to spend 60 seconds in this cubicle, correct? So the T did not change. This is still 60 seconds. But what's I? Does everybody see that I is the maximum number of customers that can be in the blue room? Well, there can be a customer here, and there can be a customer here, correct? Okay, so I is 2 customers. And then we do I equals R times T. And when you do that, you will find out this is now 120 customers per hour. Those of you who like process analysis, if you're an electrical engineer, you like resistors in parallel, if you're mechanical, all of this is that same analysis right there. And you can think of it, it's like when we were doing this right up here. Remember when we had 4 different scanning machines up there, and each of them could do 30? Collectively, it could do 120 customers an hour. Yep.
So now we can
That's exactly right, okay? So by doing this, that was the whole hope, right? The whole hope was we get a new bottleneck and we go faster. So now this room can do 120 customers per hour, which means this isn't true anymore. Okay? So now where's my bottleneck? Okay? Notice, we're looking for the lowest R, not the longest T. All right? The lowest R is this 90 now. It's not the lowest T. The T is, the 60 is still longer, but we have things in parallel now, so it changes that. So everybody cool that there's the new bottleneck? So therefore, this is now 90 customers per hour. Here's a little surprising one. What happened to my theoretical flow time?
Nothing.
Absolutely nothing happened to my theoretical flow time. My theoretical flow time says there's no waiting, so it's just how long I'm spending in the boxes. I'm spending the exact same 60 seconds in this box I used to. It's either there or there, but it's still 60 seconds, correct?
Yeah.
What happened to my utilization? That did change. We gotta be careful, we gotta go do this, right? Okay, so labor utilization, and let's just do this real quick. There's still one in there. It's still capable of doing 240, right? But now we're running 90 through it, correct? Okay, there's still one in here. It's still capable of doing 120, but now we're running 90 through it. Now, what's happening there? There's two people in there now, right? So isn't whatever's working in there, that room, if I'm running as fast as it can, both those people are as busy as they can be, and if it's not running as fast as they can, both those people are not as busy as they can be, right? So this becomes two people. Number of labors in the room, okay? Times, now, what is this capable of doing? The room is capable of doing 120, but because of the bottleneck, we're only running one. You see how this works? Did I skip one? Yeah, I skipped one. So that's 120, this is now 90. Okay, now, this is 90 over 180. And this is 90 over 120. And then you have to divide by 1 plus 1 plus 2 plus 1 plus 1. Got it? All right, let's try something a little harder. It's perfect timing now, okay? So I'm going to show you how you would do a more complicated system. Remember our